Okay, so in this video, we're going to go ahead and take a look at converting between the various forms, between rectangular and polar forms. So we'll just jump right into that right here. So the first thing that I'm going to do is I'm actually going to shift my paper down here to this little area so I have a little room to work. But the idea for convenience, I'm going to put it right here, is that we are giving you, in this case, a theta right here, an angle to rotate. Now, keep in mind, this isn't a variable, so it really could be in the second quadrant. I just don't know how far it's rotated, and some distance out here. But what we want to do is we want to make a connection between the old version, x and y, and the new version, r and theta. So keep in mind, these are our what we call rectangular version, and these right here are called our polar version. So we're going to see how those things relate to each other. Well, the clear and obvious first thing that we would be able to say is that x squared plus y squared equals r squared. So that's kind of important. So if I were to hand you x and y, then you can clearly just use the Pythagorean theorem and go grab r. That's not a big deal. If you want to, you could write r as the square root of that. I don't really see why we would want to do that right now, but that works well. So that's a way to take x and y and turn it into r. Pretty convenient. But we can also use just a little teeny bit of trigonometry, because the definition of the sine is opposite over hypotenuse, which would be y over r. But that means if you want to cross multiply, then r times the sine of theta would be y. So what you can see here is that then I have r sine theta, which is all 100% the idea of a polar look, and it's been converted over here to a rectangular look. So if you know r and theta, you can get y by taking the r and multiplying it by the sine. And by very quick, easy logic, the cosine is adjacent over hypotenuse. So again, cross multiplying, r cosine theta would be x. And so that's, again, you have r and theta as your known values in polar. And if you wanted rectangular, all you have to do is this. Now notice you have, looking for two values, x and y. So you have two different equations that help you find that. In the same way, notice over here, if you had x and y and you wanted to go to r, you can do that here as well. Now, when you go to the last part, so notice I have, this is how you find r, this is how you find y, and how you find x. The trickier part is, how do you find theta? Now, that's a little harder. So again, I could say that the tangent of theta would be y over x, and that's undeniable. So if I wanted to say what is theta itself, then I could say that theta itself is the inverse tangent of y over x. And this is 100% a valid form of logic. However, there's a little bit of a flaw, because as we mentioned in the last video, there are an infinite number of representations for that theta. And that's a little bit of a problem, because when you do inverses, they have to be one-to-one. There can be only one representation for that answer. And so I'm going to put a little star next to this, because I don't really often use this. I usually just think about what angle would create that situation, or sometimes use a little technology to get that. So this is my little handy dandy little list of values. Again, if I have x and y and I want r and theta, that's here. Or if I have r and theta and I want x and y, I would go here. So a couple quick examples. Again, not going to do very many, but imagine we could go starters in a really, really nice, easy one. Like, let's say we went 10 at 3 pi over 2. Well, that's right here, the 10th circle. I'm just going to kind of guess at it that that's about the 10th circle. I don't want to count it right now. Well, somebody else would say, well, wouldn't it have been easier for you just to go straight down 10 units? Notice that literally I didn't move to the left or right at all. I just simply went down 10 units. That would create exactly the same location. That one was, of course, very, very simple. But the next one, I'm going to go ahead and make it a little bit harder. Like, let's say we went 18 at 3 pi over 4. Well, that's not quite as obvious. So we're sitting out here at the 18th circle, right out here at the angle 3 pi over 4. And so, of course, most of us don't have that stuff memorized, but I know that x is r, there, cosine theta, and that y is r sine theta. And so what we can do is we know that the sine and cosine of any kind of pi over 4 are root 2 over 2. So if we took 18 times root 2 over 2 and 18 times root 2 over 2, you would get 9 roots of 2 in both situations. But since the cosine is in the second quadrant, the cosine is negative. And since the sine is in the second quadrant, it's positive. But that clearly makes sense either way that you look at the problem. So that's kind of a quick way to look at it. Now, I'm doing very, very nice problems here. And so please understand that sometimes you get really nice ones and sometimes you don't. So what happens if I did something in polar, and this is going to be, again, kind of weird. Like, what if they said, hey, I wanted to go to the 10th circle, but I wanted to go to 5.1 radians. So again, I could just come into my calculator. I could check my mode and make sure that I'm in the right mode, and I could do r cosine theta. That would be my x value. And then r sine theta, that would be my y value. And so sometimes we can just be a little bit lazy and we could use technology to come up with those values. But remember, x is the cosine and y is the sine. Now, of course, going the other way can be a little bit trickier for people. So what if I said I wanted to take the coordinate, say, 10 comma negative 10, and I wanted to go the other way? Well, of course, the Pythagorean theorem says x squared plus y squared equals r squared. Well, that's 100, so is that. It's 200, and so I end up with 10 roots of 2. Now, I hope you catch that what I did right there is I was just using a simple little 45, 45, 90, but as a hint, since it was a basic 45, 45, 90, and it's down here, then now we have lots of choices. Some of you would represent that as negative pi over 4 because if this is 10 and this is 10, this has to be an isosceles triangle, 45 degrees or pi over 4. Others would have chosen to write it as, say, 7 pi over 4. This is where we get into all of these different possibilities. Somebody else might have decided to just be a little bit ornery and say, well, I want to go to the angle 3 pi over 4 over in the second quadrant and rotate backwards into the fourth. Well, that's obnoxious, but it's perfectly legal and there's nothing wrong with that. And then sometimes we just get unpleasant numbers. And this is what I wanted you to see real quick, is what if we had something that was a little bit, well, actually, let me do 2 more. Let's say we went over 6 and up 6 roots of 3. So again, if we go over 6 and up 6 roots of 3, I'm using one of those special right triangles that we have done before. This is one, anytime you see that root 3, if you did the Pythagorean theorem, you would find that that is, in fact, 12. That's not a big deal. And now when I look at this, I'm going to say, I got to find that angle. And I'm going to go ahead and be a little teeny bit lazy. And I just look at the problem and I say, is there a ratio in trigonometry that would be really, really easy for me to see? And I can see on this one that the cosine is 6 over 12 or 1/2. So if the cosine is 1/2, when is the cosine 1/2? There it is. It's the angle pi over 3. So I took the ratio here to come up with that angle, and that was a pretty slick, easy way to go. But again, many, many representations. We could have said, hey, I'm going to go 12 at 7 pi over 3 because I wanted to go more than a full circle away from it, and that's all good too. So sometimes I have a situation where I can reference special right triangles like what we have done in previous classes, and sometimes I want to go ahead and just think about what those ratios are. And last but not least, right here for point Q, we're just going to do one last one. And I'm going to make one that is definitely not special. Like, let's say it was -2, 1. Well, this is not one of the 30, 60, 90s or 45, 45, 90s that you studied back in class. But again, if we did a squared plus b squared equals c squared, we'd get -2 squared is 4, 1 squared is 1, it's √5 is the radius. But then what do we do as far as that angle goes? Well, it's -2, 1, which makes this √5. So there's a couple of ways that we could do this. What I would choose to do probably is I'm going to use my calculator and know that the inverse cosine is defined in the second quadrant. So I'm going to hit the inverse cosine of -2 over √5. And that is going to give me an error if I didn't catch that. But there's my angle, 2.677. And that's great. Perfectly good answer. Although that's just one representation. Now notice that if I had tried the inverse sine of 1 over √5, which seems like it would be a good idea, the problem is my calculator believes that the inverse sine has to be in quadrants 1 or 4. Well, you can see how this could get a little bit tricky. It gave me the wrong answer. So it is nice that they have built into our calculator something a little bit special. And I usually hesitate to show this to people, but here it is. See, right here under angle, I hit second apps, which is angle. And if I go down to here, this, notice number 6 says R arrow P theta. That says rectangular, turn into polar. Please provide me with theta. So notice I'm literally going to type in the coordinate -2, 1, and the calculator is going to take this polar form, rectangular form, and turn it into the polar form and tell me what theta is. And again, that's very, very safe because my calculator understands where things should be and it will actually represent it correctly. Now, of course, if I wanted it as a negative angle, no big deal. I'll just take 2 pi away from it. This would also be a valid answer to that. And so that's a little way that we can actually look at this through a variety of lenses. Hopefully that makes sense for converting those coordinates back and forth. I wanted to keep this video relatively short, so that's where I'm going to stop this thing. So I will see you back in class.